Okay, so welcome everyone. I'm Jeremy Simon, a longtime Enable volunteer and 3D printing enthusiast. I'm also the founder and CEO of 3D Universe. We are a value-added reseller for 3D printers and other types of digital fabrication things, as well as materials and supplies. And we also make these assembly materials kits that a lot of our Enable volunteers like to use to make it easier to put these hands together. So please forgive the plug there. There may be a few more of those throughout here just because there's some things that I think might be of interest to you folks. We do try to support the community as much as we can. We offer discounts, so feel free to send us an email, info@3duniverse.org for more information. With that, we'll get started. So today we're talking about 3D printing best practices for Enable volunteers. We're going to cover a lot of different things today. We're going to talk about materials and the hardware side of things and the slicing and orientation, all kinds of different parts of this process. So I'm going to go through this whole presentation. I'm going to give you a couple of demos to show you these things. Please share your questions as we go along here in the chat. And we're going to get to those at the end. We'll have some chance to have open discussion about all of this. So here we go. So first, we're going to talk about getting the STL files, just because before you can print anything, you gotta have the files to print. And this is something that a lot of people ask questions about. So generally speaking, all Enable designs, at least all the current ones, can be found in the Enable Devices catalog. And these links are all going to be shared after the presentation in the recording. And so this is on the Enable Hub, and we have basically a wiki database there of all the different designs, and each one includes all the links you need to the STL files, as well as instructions and video tutorials and everything that goes with that design. So that's the place to start. Now, there's three ways, generally speaking, of getting the files that you need to feed your 3D printer. That is STL. That's the format we want, is STL files. And the first and easiest way is you go to the page, usually on Thingiverse, and you download the STL files there, and you put them into your slicer, which we're going to look at today, and you scale them using the scaling tool in your slicer, which is very easy to use. I'll show you. And that part's easy. But you'll find some designs, like for example, our Unlimited Phoenix hand, you go there in the Thingiverse and you don't see any STL files. All you see is an SCAD file, and people say, what do I do with that? Well, that's because it's designed for the Thingiverse customizer, which means that it's sort of a parametric design. It can be scaled in different ways, for example, scaling the overall design up, but keeping the hole size the same for screws or things like that. So if sometimes, unfortunately, the Thingiverse customizer isn't working. It happens to be down a lot. So if you click that button in Thingiverse that says open in customizer and it doesn't work, what you can do is download that SCAD file. You have to download a copy, it's free, of Open SCAD. And there is a video tutorial for how to do this. And I have, again, the link here, and that'll be shared with this recording. So you can download OpenSCAD, you can load in that SCAD file, and you can put in your parameters, different measurements, whatever, and it will generate the STL files for you in the scale that you need. And then all you have to do is bring them into your slicer and print. You don't have to scale at that point. So those are the three different methods of getting your STL files for printing. You can just download them straight from Thingiverse and scale them in your slicer. You can use the Thingiverse customizer to generate scaled STL files by putting in your measurements, or you can download and use OpenSCAD to do the same thing. Now, once you have your STL files, like I said, the most common method is you're just going to download them from Thingiverse and you're going to scale them in your slicer. So let me show you what that looks like real quick. If we go over to Cura, I'm using Ultimaker Cura. This is, as far as I'm aware, the world's most popular slicing software, but there are many others. So today, this is what I'll be showing you. If you're using a different slicing platform, there's a very good chance that whatever I'm showing you, there's some equivalent in that slicing program because they're all very similar. So hopefully you'll have the same tools available to you. I just happen to be using Cura. So if we just bring in a file here, I'll just grab an STL file, and this happens to be one of the old Gauntlet options, or what we used to call Gauntlet. We're calling it a cuff these days, for the Cyborg Beast design. And if you need to scale this part, all you have to do is select the part, and then over here on the left side, you have tools, and this one right here is the scaling tool. And by default, this box would be checked. It says uniform scaling. Most of the time, that's what we do. We just want to scale the whole thing to, let's say, 120%. So if I put in 120%, boom, the whole thing is scaled to 120%. It's that easy. Every once in a while, you'll have to do non-uniform scaling. Maybe you need to have a device that's extra long. So the Z factor might be a different percentage than everything else, and you could sort of stretch it out that way. So you can do non-uniform scaling just as easily if you figured out what the right, scaling measurements are, that's a different tutorial. I actually just created a new one the other day, so you'll have that soon in the hub. But the scaling process is as easy as that. You bring in your model and you select your scaling tool and you put in a percentage, which you've already figured out through our virtual fitting process covered elsewhere. And the scaling is done for you. So it's that easy. Let me switch back to the presentation. All right, so let's talk a little bit about hardware. Now, first, somebody asked me actually just earlier today about the differences between the different types of 3D printers. So we better cover this real quick first, because everything we're going to be talking about today is really related to what we call FDM 3D printing, which stands for fused deposition modeling. It's essentially, extruding melted thermoplastics in layers, building up from a build plate layer by layer. And this is the one that most of you are familiar with. These printers are very affordable. It's very accessible. There are all kinds of different printers available in different price points, and it offers the widest choice of materials. And we're going to be talking about that more later today. There's another one called SLS. This stands for selective laser sintering. And this is where you use a laser to sinter layer by layer a powdered media. Usually it's nylon, but it could be other materials. So it's a fine powder, and you basically have this sort of a tank full of this powdered media, and you're using the laser to sinter one layer, and then it sort of brushes a new layer of this powdered media over, and it sinters the next layer, and then it puts another layer, and it goes layer by layer. But the result is that as your object is being built in this powdered media, it's being fully supported in that powdered media. So you don't need what you would normally consider supports. Your object is fully supported as it's printed. So you can print all kinds of amazing things. But SLS prints are they tend to have a very rough surface. And I'll show you this. I've got some photos I'll share with you in a moment that show you these different types of printing and what they look like. But SLS prints tend to have a very rough surface finish, not very good for moving parts when you have to have things that move smoothly with one another like we do. Also, SLS printers tend to be very expensive. As far as I'm aware, the least expensive one is somewhere north of $10,000 as far as what I've seen. So they're pretty pricey. Then we have SLA, that stands for stereo, I got a typo there, stereolithography, uses a light source, could be LCD, it could be DLP, et cetera. Some use lasers to harden a photosensitive liquid resin layer by layer. So in this case, you have sort of a pool of resin, and your print sort of lifts out of it as it cures layer by layer. And I'll show you that in the photos. But these printers are becoming a lot more affordable and a lot more accessible. So a lot of people are asking about this. Now, the first thing to know about SLA prints is that they're extraordinarily high quality, and I'll show you that in a moment, but they have relatively few materials available. You only have certain resins to choose from, and most of those resins tend to be, number one, not really well suited for enabled devices. They tend to be sort of brittle. Now, there are tough resins. There are resins that have the kind of physical properties we want, but then you run into the problem of them becoming rather expensive. Some third-party resins are coming into the market, so this might change. We might have affordable options for SLA with resins that would work well for Enable. Right now, it's not something I'd really recommend for Enable devices unless you can afford those really high-end engineering resins. Generally speaking, FDM is what we recommend. FDM is what most of you are using. And so with that, we are going to move on and focus on FDM printing. But before I do that, I'll just show you a few of these photos, like I said. So I've got a couple of examples here. If we look at kind of just general 3D printing, this is the one all of you know. An FDM printer is doing just what you see here. It's putting down melted plastic layer by layer, building up from the build plate, building up vertically. Most of you already know this. So the SLS, now let's see, I think I had one of these. No, I might not have put this into my right album here. So I don't have an SLS print to show you right now, but SLA prints, this is what it looks like when it's printing. It's coming up out of this vat of liquid, and you can see this sort of scaffolding of support that you may or may not need, very much like when you're FDM printing. And those just break off very easily. They're connected just with a tiny point on the object. And after you break those supports off, you're left with an object of incredibly high quality, which you just, like if we zoom in here, you could not get this out of an FDM printer. So when you need the ultimate level of quality and detail, that's where SLA shines. I would not say that it's the first choice for Enable devices though. So determining which materials you can use. You have your printer now. Let's assume you have an FDM printer. Now you're wondering, what materials should I make my Enable devices out of? Well, the first question is, do you have a heated bed? Because if you don't have a heated bed on your printer, then you don't have a whole lot of choice. You're pretty much limited to PLA, some of the enhanced forms of PLA, maybe TPU for flexible printing if you have a certain type of extruder, but you're pretty limited. Mostly those printers are designed for PLA. And as we're going to discuss shortly, PLA is not really the ideal material for enabled devices. I'll explain why. So let's hope you have a heated bed. If you haven't bought your printer yet, I highly recommend one that has a heated bed. I also recommend that you avoid the mini type 3D printers. Some people like to start off with an entry level sort of mini printer, real nice small form factor that can sit on a desk. The problem is that the bed is so small that you're gonna have a hard time making some of the enabled devices. Best case, you're gonna have to do a whole lot of print jobs just to get one device made because you're gonna have to print the parts one or two at a time. Worst case is some individual parts might not even fit for some of our designs, and you might have to figure out how to split those parts into multiple pieces, and it just makes things a lot more difficult. So a print bed with just an average sort of a size, let's say 8 by 8 by 8 inches or something around that, or larger, is highly recommended. A direct drive extruder is very beneficial if you plan to print flexible materials. This means that the extruder, the gears that are grabbing the filament and pushing it through are right next to the hot end, right next to the nozzle. There's not far for that material to travel from the gears that are pushing it to the hot nozzle. They're right next to each other. Whereas some printers use a Bowden tube that extends to a feeder mechanism on the back of the printer. So the extruder, the gears are on the back, and it's pushing the material through the Bowden tube up to the hot end. Those printers make it a lot more difficult to print flexible materials. You can sometimes print flexibles that are sort of semi-flex that go down to maybe a TPU 95A short hardness. But if you try to go softer than that, you're gonna have a hard time. So a direct drive extruder is very beneficial, as some of our designs do incorporate flexible materials. An enclosed build area is also helpful for some materials. Doesn't really matter for PLA and the enhanced PLAs, but as you start to get into some of the other materials like PETG and ABS, we're going to be talking about some of these others, and nylon, those tend to warp, and having an enclosed build environment so that you can keep that build chamber warm helps tremendously to get you better printing results and avoid failed prints. And you also want to think about your nozzle size. Most printers give you a choice of what nozzle you're going to print with. And if you use a 0.25, a small nozzle, 0.25 millimeter nozzle would be really good for fine details, for doing really, really super fine details, like maybe if you had extruded text that was really thin. That's where you might want to look at using a 0.25 millimeter nozzle. But otherwise, it's going to make your printing take so much longer, and you really don't need that for printing enabled devices for the most part. The 0.4 millimeter nozzle is what's standard, and that's what most of us use, and it's good for most cases. That's kind of your average print quality. You can get really high quality prints out of it, and for the most part, our enabled designs don't need anything more than that. But you could also think about going up higher. You could put a 0.8 millimeter nozzle or even larger. And honestly, for a lot of our enabled designs, you're not going to see a big difference because you can still do thin layers horizontally for the layer thickness. But as far as how much ground you're covering with each layer, think of a lawnmower. The bigger your mower is, the fewer times around you have to go on a field. It's like that. So that when you're doing a layer, it can be covered a lot more quickly with a larger nozzle. And as long as you don't have really fine features, again, like extruded text or symbols with fine corners and things like that, you're not really going to see a difference. So think about maybe using a larger nozzle. It'll drastically speed up your print time without impacting things too much. Okay, so now we get into materials. There are a lot of materials to choose from in the FDM world. That's the beauty of FDM printing, and more are coming every day. That's the exciting part. With your very same hardware, you're getting access to all these new materials that keep coming into the market. So the possibilities just keep expanding, and that's wonderful. But it does open up a lot of questions. Where do I start? What do I use? What can I or can't I use with my printer? So this diagram is kind of a helpful overview here. You can see that the bottom of the pyramid, you have what are called commodity thermoplastics. And then in the middle tier, you have what are called engineering thermoplastics. And then in the upper tier, you have what are called high performance thermoplastics. And then they divide them down into amorphous and semi-crystalline. And we're not going to be getting into too much material science today, but what's more important is these three tiers. For the most part, the kinds of FDM printers that most of us are going to be using in the Enable community are desktop FDM printers that for the most part are going to be capable of dealing with the lower two tiers that you see here, commodity thermoplastics and engineering thermoplastics. And engineering thermoplastics, to what extent it'll cover that depends on your printer hardware and its capabilities. So may or may not be able to deal with those. Most of us here are not going to be dealing with a high performance range of materials because you need a really, really high extruder temperature and often need an actively heated build chamber and things like that that a lot of us just don't have. So we're not going to be dealing with any of those today. We're going to be focusing mostly today on the highlighted four materials here: PLA and some variants thereof, ABS, PETG, and TPU. These are by far the most common materials that you run into. A lot of people like nylons and things like that, and there's some benefits. We're not going to get a whole lot into that today. I think I have a slide on it, but mostly we're going to focus on these materials because this is what most people deal with in Enable. So let's start with PLA. Most of you already have heard of PLA, maybe have used it. It is wildly popular in 3D printing, and there's good reasons for that. It's very easy to print. It does not tend to warp, no matter your environment. You can have an open build chamber. You can have all kinds of drafts going on. It's just happy to print just as nicely as if you have a warmer environment without any drafts. So it's really a nice material to work with. It's widely available, probably for that reason. It's very inexpensive, again, because so many sources are available for it. It's environmentally friendly. It's made almost entirely from plant-based materials and therefore non-toxic. You do not need a heated bed. So pretty much any 3D printer on the planet can print PLA. So it's really a wonderful material for a lot of reasons. The cons would be, though, that it is a fairly brittle material. So it's hard, it's nice, it does have strength, but it's brittle. It will break under stress. It doesn't have a lot of give to it. And it is going to deform in hotter temperatures. It does not have a very high temperature resistance. So for example, if you were to leave an Enable hand in a hot car on a summer day, you will come back to find that hand in a very different shape than when you left it there. It will be somewhat melted. So PLA, for that reason, is not a great choice. Even though it is so popular, it is not the material we're recommending these days for Enable devices, unless you know that it's not going to be in that kind of a warmer environment. There are a lot of enhanced PLAs now. There's Tough PLA and PLA Plus and PLA High Impact and all kinds of different enhanced PLAs, and those are really nice. They're just as easy to print as normal PLA. They're widely available also. They're growing in popularity. They're also inexpensive, often the same price as normal PLA, but environmentally friendly, non-toxic, pretty much the same benefits. The only difference is that they're 2 to 3 times as strong. So you kind of got to ask yourself, well, why would I use normal PLA? Honestly, from speaking for myself personally, I don't. I almost never use PLA these days because Tough PLA is my go-to material. There's just no reason to go to PLA except that it's available in more colors. People tend to offer these enhanced PLAs in a smaller range of colors. So that's the only reason I would go to PLA, is if I need something in a particular color. Otherwise, I use Tough PLA. I'm not talking for Enable devices now. I'm talking just for my general printing needs. I still wouldn't recommend these for Enable devices necessarily because of the temperature issue. Tough PLA and these other enhanced PLAs are generally no better than standard PLA when it comes to temperature resistance. So still not an ideal choice. ABS. Now this was really popular back when desktop 3D printing got started. A lot of printers were kind of optimized for this. Flash Forge printers, for example, when you buy one, it would come with Kapton tape on the build plate, which is designed for ABS to stick well to it. And, there are some nice things about this material. If you've ever, played with Legos, this material. That's the material we're talking about. It's a petroleum-based, plastic that has that typical plastic feel to it. Good impact and wear resistance, again, from Legos. Those are very tough. You can kind of bend them a little bit. They have a little bit of give to them, but they're very strong. Higher temperature resistance, significantly higher than PLA, so they will hold up better. It's readily available. You can get it anywhere. One of the nice things about ABS is it can be treated post-processed with an acetone vapor treatment, and you can actually smooth the outer surface. It kind of melts the outer layer of the plastic, and you can get a very smooth, kind of glossy part that looks like something that was injection molded. So that can be very useful, even with Enable devices, possibly. And it produces a very attractive surface finish for that reason. But there are cons to this material. It can be very challenging to work with because it definitely has a tendency to warp. There are some adhesives that we'll talk about a little later that will make it much, much easier to print ABS and other more advanced materials. It may produce some harmful fumes. You got to be careful with ABS and some of these other more advanced materials. You might want to have some kind of filtration on your 3D printer, make sure you have good ventilation in the room, things like that. May not be suitable for prolonged skin contact. And here's where we start to ask, is this a good material for enabled devices? Well, that could be debated. I have used ABS several times for an adult male that I make devices for because he loves that smooth, post-processed treatment that I can give it. And it is padded, so the plastic parts are not coming into direct contact with his skin. And he's an adult; he can, take care of himself and be safe about it. I probably wouldn't choose to use ABS for a device for a child. That's just me. Other people might feel differently. TPU. Now here's an interesting material. This is a flexible material, and it's a lot of fun. It has really good impact and wear resistance, so it's great for things that might be involved in a lot of movement or friction or vibration dampening. Great for some of our enabled designs have incorporated this in the hinges, and it makes for much quieter hinges than some of our other designs. But it can be a very challenging material to work with, and that goes back to what we were talking about regarding a direct drive extruder, which can be very helpful for printing these flexible materials. Not necessarily required, but very helpful. So something to think about as you're looking at a 3D printer, or maybe your next 3D printer. And then there's PETG, and ultimately this is the recommended material for enabled devices as of now, at least in my mind. Some might disagree, but this is the material that I have been recommending and a number of others have been recommending because it has a lot of good qualities. It's a lot stronger than PLA, much stronger. It's also environmentally friendly, more so than ABS. It's non-toxic. It's used, for example, in a lot of water bottles and those kinds of products that we're familiar with. It has a much higher temperature resistance than PLA, so it takes care of that issue for us. But it's not so high that you'd have trouble thermoforming it. It would be very difficult to thermoform an ABS part. It definitely is possible to thermoform a PETG part. You have to use a little bit more heat, a little more time than a PLA part. So if you were using, for example, the hot water method, this is covered elsewhere, you might have to submerge a PLA part for 5 seconds and it starts to deform. A PETG part might take 30 seconds, but it still works quite nicely because you get the benefits of the strength and that temperature resistance later on. Another nice benefit is it is available in skin tone colors from 3D Universe. Here's another one of those plugs, folks. Hope you don't mind. But we designed these and have these produced specifically for the enabled community. So we went and queried the community about which skin tone colors might, best cover the widest range of people out there. Obviously, we can't cover every skin tone in the world by far, and kind of went through a voting process from a whole bunch of different colors. And these are the ones that the community sort of decided on for a first run. And so we offer these 4 different skin tone colors in our PETG, both in 1.75 millimeter as well as 2.85 millimeter. So hopefully that's helpful. I understand it can still be expensive to get these to certain other regions in the world. We're working on improving that as we go. Some of the cons of PETG, it can still be rather challenging to print, but again, we're going to cover that in a little while as far as using the right adhesives and things to make it easier. It tends to be a little more stringy when you print it. You'll see like strings running between your parts and things like that sometimes. Part of that is just about getting really good quality PETG. I will say that our PETG tends to be a lot less stringy than others. That's part of the reason we developed it the way we did. And it also is not as widely as available as PLA, perhaps. We're trying to change that. That's why we're making these skin tone colors available. It does cost a little bit more than PETG, but it's not too bad. And we talked about how it can be a little bit stringy, but as long as you have the right settings, tweaking your retraction settings and things like that, which we have covered on our website, you can get pretty good results with PETG. So that's the recommended material overall for a device that's going to a recipient. Not necessarily if you're doing your first test device or something like that, but if this is something that you hope somebody is going to end up using, PETG is recommended. All right, now we've got our 3D printer, we've picked our material, we've got our STL files, and we've gone through our scaling process, and we've figured out how we need to scale them. Now we need to get ready to print them. And the first thing you want to think about in printing is part orientation, because the part orientation is, most of us think about part orientation as primarily affecting like print time, like, how can I get this printed most quickly, or how can I use the least amount of space on my build plate or something like that. But that's not really what you want to be thinking about. What you want to be thinking about is the orientation of the layer lines and how that's going to affect how that relates to the stresses that are going to be placed on that part and what's going to yield the best strength overall. So this is worth taking a look at. Let's pause for a demo here. If I go back into Cura and we kind of reset our scaling here, and we look at this. So I just grabbed this. This is an old version of a cuff that is probably not used very much anymore. It goes with the Cyborg Beast design, but it's helpful to illustrate a concept. So when I don't know if you noticed, when I first dragged this file in, it came in this orientation, which kind of suggests to you that that's the way the designer wanted you to print it, right? So you'd kind of think, okay, well, they want me to print this vertically. And at first glance, that looks nice. That looks like it's a good way to print it because you've got it looks like you have a flat bottom here to connect with the bed, which is something that we know we want when we're 3D printing for good bed adhesion. And even when you look at like some of the spaces in here, like how these are angled upwards, that kind of suggests that it's meant to be printed this way because you can print as you're sort of stepping up this way, layer by layer. Printers can do that without supports. So that all suggests that it would be done this way. Well, let's do an experiment here. I'm going to go ahead and slice this just using draft settings, so it'll be quick here. And slicing is basically taking your model with your designated settings and it's dividing it into layers and instructions for the printer on how to print each layer and where to move on each layer. And so it's going through and slicing that right now. And as soon as the slicing is done, we get a chance to preview it. And that's what I want to show you here. So let's just take one more moment. There we go. All right, so now we'll go into preview mode. And it's got to render real quick. Okay. So here we go. Now we've got our model, and at first glance things are looking okay. But here's what I want to show you. Let me reposition this a little bit. So let's look at these hinges here. You can actually see when you really start to zoom in here. You can see the individual layers, and over here you've got a tool that you can use on the right to kind of scroll through these layers, and you can see what's going to be printed on each one, including your outlines and your infill and everything. And if we get up here into this hinge, look what's happening. If you look right there, that's where this device is going to break because you've got so much stress on this hinge and you've only got these two little spots of material trying to connect layer to layer. And your parts are always going to tend to break across the layers or along, the direction of the layers. Sorry. So the layers are just going to tend to split along the line that they were printed. They're not going to tend to break perpendicular to those layers. So even though it would look like you would want to print this part vertically, that's not true. This part we would want to, let's go back to our prepare mode. And what we would want to do is go to our rotate tool over here and flip this part. You can use these little arrows here to flip it 90 degrees. There we go. And we would want to print it in this orientation, okay? Now, that opens up some other issues that we're going to cover later. So for right now, all I wanted to show you is the orientation thing. And so we'll come back to this a little later. Okay, so now we get into slicing. Now you've got to, sorry, I adjust my camera. All right, so now we get into slicing. Now we need to talk about the different settings that you get into for preparing your print job. And the first one to talk about is layer height. How thin do we go? Well, printing with thinner layers takes longer, but it yields smoother surfaces. So when you have moving parts, you're gonna have less friction. That's a good thing for enabled devices. So for the most part, we recommend using somewhere between 0.1 and 0.2 millimeter layer heights for enabled devices. It's not set in stone, but that's what we generally recommend. I usually use 0.15 millimeters myself. Sometimes I'll use 0.1. I usually don't go to 0.2, but a lot of people do, and it's okay. But the thinner layers are nice because it does make them move more smoothly and more quietly. I personally, I don't care about print time so much. I'll set up the print job and just let it run overnight. So I'm happy to let it go at the slower pace and get a nicer print quality out of it. So here's some examples of things, the same little froggy printed at different layer heights. If we look at the 0.05 millimeter, that's 50 microns, 0.05 millimeters. You can see it's a very smooth surface. You almost can't see any layer lines in here. You can maybe barely start to see a little layering on some of the curved or slanted surfaces, but it's awfully hard to see any layering here. Then you go up to a zero 0.1 millimeter. This is what I typically use, this or 0.15 for enabled devices. And again, it's pretty hard to see any layering. This gives you a really nice smooth part. You can start to see a little bit, again, on the curves of the eyeball, on the curves of the toes, on the slant of the arms, just a little bit of layering there, but really smooth, good quality overall. But if we jump up then to 0.27, this is beyond what we recommend for enabled devices, and you can see why. Clearly visible layer lines, and you can just imagine two parts like this moving against each other. It's going to feel like, when you walk with corduroys, it's just going to be kind of vibrating, won't work too well. And then we go to 0.34, but you can see why 0.34 wouldn't be a good idea. I'm going to move on. Shells and wall thickness. You want at least 3 shells. I usually say 3 or 4 shells for enabled devices. And you can see in the image below an example of what that means. The outer walls of your image, and this is all the way around. This is sides as well as tops and bottoms. Whatever the outer shell of your parts is, it's going to be this thick. So if you look at 2 shells on the left, that's a little bit too thin for comfort. So we recommend 3 or 4 shells, or walls, sometimes it's called in the slicers. Or sometimes it just asks for your wall thickness, and that's going to depend on your nozzle diameter. So if you're using a 0.4 millimeter nozzle, which is what's typical, and that's what the 3 or 4 shell recommendation is based upon, that means we're looking for a 1.2 millimeter to a 1.6 millimeter wall thickness, generally speaking. Infill percentage is another important setting. We recommend somewhere between 30 and 40% infill. You can see down here what 30% looks like on the inside, and you can imagine 40% being between the 30 and the 50 here. So that's the range that we like to see for enabled devices. Too much more than that, and your device is going to be heavier than it needs to be without enough added strength benefits. It's going to tend to break at the, at the joints or things like that anyway. So you're not really getting a lot of benefit, and you're just adding weight. So you don't want to go too much higher, too much lower than 30, and you start to get a weaker part overall that might have breakage. Infill style is also an option. A lot of slicers just take care of this for you. The default is usually something like what you see here as rectilinear or triangular, and anything like that is fine. Hexagonal is fine. Any of these patterns where you see that it's crossing and you see that grid pattern is fine. You get a nice strong infill pattern. You want to avoid things like concentric that you see in the lower right. It just doesn't give you the same kind of strength and rigid structure on the inside. Several of our enabled designs, and I dare say most of them nowadays, are designed and to be optimized to print without supports, which is really nice. Most printers can handle overhangs up to 60 degrees or so without supports. I know that might be a new term. We're going to talk about that in a moment, overhangs. Bridging can also be used to help with this, and that might be another new term for you. So we're going to cover those 2 new terms next and how they relate to supports. All right, overhangs. Most 3D printers, as I said, can handle up to around 60 degrees. The image that you're seeing in the lower left there, that whole thing was printed without any supports on a standard FDM printer using tough PLA in this case. And if I flip it and show you the underside, that's what you're seeing on the right there. As you can see, it printed really cleanly all the way up until in here. And what you're seeing in here is about 65 to 70% or 70-degree angle. So, again, 60 degrees is pretty conservative. And most people are looking for really nice surface finishes on their parts all around. Think about what we're doing. If we're printing a palm and you've got the inside of that palm, and yeah, it's going to need to do some, some heavy overhangs in there. You might get up into this sort of territory where you have messiness like this inside of that underside of the palm. Well, we don't care because we're going to be covering that with adhesive foam padding. So, you have to think about the intent of your part. It might be perfectly fine to go up to 80, 85 degrees without using supports. And then you have bridging. If you're connecting between 2 points that are at the same height, the printer can actually bridge across those 2 points as you're seeing in this image. So it can sort of stretch the material from one point to the other, and then it sticks on the other side, and it can hold itself there, especially if you're using the right fan speed for, to cool it really quickly as it goes. You can, as you can see here, we're getting bridging all the way up to a distance of 110 millimeters on that top one. You can just barely start to see a couple of threads start to droop there on the top. But certainly, 100 millimeters or so can be accomplished without supports if you're connecting 2 points of the same height. All right, so then there's also something called build plate adhesion, and this is in most slicers. You can choose your build plate adhesion method. And there's generally three types of build plate adhesion, or I guess you could say a fourth type is none. But a raft is one option. It's one that I almost never use, and I would say avoid it if you can, just because it adds a lot of printing time. What it does is it prints a number of layers underneath the entirety of your printed objects, as you can see in the image here. And then after your print's done, you need to sort of peel that off. And it does, for the most part, it comes off nicely if your slicing settings are calibrated properly and your printer is calibrated properly. But it does add to your print time. It adds to the amount of material that you're using. And I just don't think it's necessary in most cases. If you're using the right material and the right kind of adhesive and the right kind of build surface, which we'll get into shortly, you shouldn't need a raft, but it's there as an option if you like. If you're really dealing with a difficult material, it can help to give a good surface for it to stick to and maybe avoid warping. I think the adhesives are a better way to go. Then you have something called a brim. I do use this from time to time, but I do try to avoid it. A brim is where it's connected to the object at the base, as you can see in the image at the bottom there. It extends out from the base, but it is connected to your object so that after your print, you take it off the build plate, you do need to remove the brim. You have to kind of go around with an X-Acto knife and kind of trim the little bits that, you know, might not come off cleanly. So again, if I can avoid it, I don't use it. It does help with materials that tend to warp, like PETG, ABS, nylon, etc. Again, with the right adhesive though, even with those more difficult materials, I usually don't use a brim, and I'll show you that shortly. And then you have what's called a skirt. This is what I typically use. This is really simply there to kind of clear out the extruder, make sure that it, you know, if there were any, you know, if there was any remains of a previous material in there, or if maybe your material wasn't fully primed all the way up to the nozzle, if maybe kind of settled back a little bit. The skirt just, all it does is extrudes a couple of loops of material outside of your object so that you know your material is coming out clean and smooth, and then it proceeds to start printing your object. So I really like using a skirt for that reason. It's not connected to the object, so you take your object off the build plate and the skirt comes right off, you just throw it away. It doesn't add any time, it hardly adds any material. So I usually have the skirt enabled as an option. All right, so general recommended settings, we've covered this, but just in summary, layer height 0.1 to 0.2 millimeters for enabled devices, shells or outer walls 3 or 4, or if you're doing something other than a 0.4 millimeter nozzle, you want somewhere around a 1.2 to a 1.6 millimeter wall thickness. You want about 30 to 40% infill. You want to, you know, address all the temperatures and speeds and retraction settings, et cetera, based on the material that you're using. So we'll talk about some of that in a little while, but that should be provided with the material that you get. You know, the material manufacturer will give you the settings or give you a profile that you can use, so that you shouldn't have to mess around with that too much. And then one last thing, and this is incredibly important. Always, always, always preview your G code before you print. I cannot stress this enough. Nothing will save you more headaches and more wasted time and wasted material and failed prints and frustration than previewing your G code before you print. So absolutely get in this habit. And I'll show you why. Okay, let's get into another little demo here. I'm going to get rid of this part for a moment. And let me grab a different part. And this is one that I've been working with John Schull on in a different group, where we've been doing some design work on masks. This one is for a vacuum formable mask that we're working on. And this is a mold that we're printing. And so he sent this model to me. You drop it on the build plate and it looks good. So I would go ahead and set up my settings and get the sort of the layer, that stuff that we just went through. Let's just pretend I already did that. I'm going to go ahead and slice this. And we've got it on draft settings here for this demo, so it should go fairly quickly. But again, I want to show you why it's so important to preview, because it can be very deceiving. Even if you kind of, you know, pan around, everything here is looking pretty good. You know, I mean, we've got a nice flat surface. Yeah, I mean, everything looks like this should be no problem. Now the slicing is done. Let's take a look at the preview. And again, once the preview renders here, the very first thing you want to do is scroll all the way down to the first layer. This is the reason we're using the preview. And if I go down to layer 1, look at what becomes immediately apparent. Oh, that first layer doesn't make full contact with the bed. So that bottom surface wasn't actually flat, even though it looked like it. It maybe had a little bit of a bulge to it that I couldn't see. And if I was to try to print this, it would print that layer, and then it would go up to layer 2, to 2, there you go. So you see it's trying to print outwards further, and then layer 3, it goes a lot further, and layer 4, only when it gets to layer 4 is it printing the full surface. Well, I'm using 0.2 millimeter layer heights here, so that means that I'm already at 0.8 millimeters off the bed, and it's trying to print. That stuff is not going to stick, and so this is going to be a failed print. And I can see that just by looking at the first layer. How do I fix this? Well, it's easy. I mean, I could go back to the CAD tool and fix my model. That would be the ideal way, but there's a quick fix. Just go here to your Move tool, and on the Z-axis, vertically, I'm just going to drop it down. I'll take it down 1 millimeter. And what that's going to do is kind of move it just slightly below the build plate, just essentially cutting off the bottom part of your object, and you will end up with a perfectly flat surface. And so after you then slice it and you go into the preview and you go down to layer 1 again, you'll see it's going to show the full layer 1 for this. I will edit these pauses out of the recording, but you guys have to sit and watch it. So here we go. Now if I scroll down, it's still rendering, there we go. Scroll down to layer 1 and look at that. We got a beautiful layer 1 covering the entire object. That open slot in the middle is intentional, that's part of the object. And you can see our brim around the outside. This is going to be a successful print. And I can then scroll up and look at everything else. My infill looks like it's enough, and I can look at the thickness, and everything looks like it's going to print well. Now I'm ready to print, okay? So very, very important to preview your G-code to avoid lots of failed prints and headaches, especially when you get into some of our earlier designs where maybe folks hadn't gotten so used to how you prepare parts for 3D printing and make sure they're oriented properly and have a flat bottom and all that. Some of those earlier designs have parts that you really just can't print without manipulation and adjusting them a little bit. All right, so now let's take another look at this cuff object that we were looking at before from a couple of different aspects. Now, we already looked at why this is not a good orientation to print in, because we would have some strength issues because of the layer orientation, especially near the hinges. So let's go ahead and reorient. We'll just spin it around here. Let's rotate it like this, and then rotate it like this. Okay, and now it looks like that would be a flat surface. The first thing we're going to do is check to see if that's the case. We're going to go ahead and do a slice, and then go to preview. And we'll scroll down to our first layer, and we can immediately see that we are not making good contact with the bed. We're only making contact along this portion here. So that's something that we have to fix. So let's go back to repair mode. Now, if you select your model and you do sort of an orientation, the orientation tool here, the rotation tool, they have a couple of tools here in Cura. You can reset the rotation, that'll set it back to what it was. But they also have a lay flat tool. So if I click that, let's see what it does. Doesn't look like it did a whole lot of anything, but let's go ahead and slice and see if that improved the situation. Preview. Okay, well, it did improve it. It sort of rotated it a bit so that this side is now making contact as well, but it's not making contact all the way to the rear part of the object. It's only the front. So let's see what else we can do. Let's go here. And this is, you know, if we kind of just spin around and take a look at this, you start to see that what you're really dealing with is just a modeling issue. This just wasn't really designed with a flat surface to be printed in this orientation. And one way that we can fix that is just to select our object, use the Move tool over here, and just move it negative on the Z-axis, let's say 1 millimeter. See what that looks like. Oops. And it just drops it down a little bit. So it is going to cut off, that it might be too much. Let's try negative 0.5. And so what it's going to do is it's just going to ignore anything that's below the bed level, which is essentially just slicing off that part of the object. And it'll start printing where the bed starts. So if we slice that now, and go back down to layer 1, now we're talking. Now you can see that it's making contact all the way along both sides. And as you scroll up, it's building cleanly up from those spots. Now, we still have to think about supports. Okay, well, you could get away with doing this without supports. The main issue is going to be these slots actually in here. And the reason for that, if you zoom in, you can see this with the layer preview. Now we can do bridging, so you might think, well, why can't bridging handle that? But if you scroll down to that point, what you'll see is, let me get above it, as it starts to build out across that, see, it's not going all the way across. And the reason for that is that the 2 points on each side are not at the exact same height. That upper surface has actually got a little bit of a curve to it. And so it has to sort of build its way across. And those parts right there are just not going to work. They're going to just fall down because you're printing in midair. So that's where you're going to have some messiness. And for that reason, if nothing else, even though you could print the rest of this, as far as this part on the inside, that could be done without supports because it's building up to that. And if you look up on the top portion, these areas where the tensioner pins go, those can also be printed without supports, because if you look at the shape real closely, you're stair stepping, you're building up gradually, and the printer can handle that. So there's no problem there. But let's say that we did want to print this with supports to deal with that slot issue. So we'll go back to our prepare mode. And let's go into our slicing settings, and we'll just turn on supports. We'll just go with the default settings and see what happens. All right, so let's just say we're going to use our build material for the supports, nothing fancy. This is what you would do if you have a single extruder printer, which is common for most folks. You do not need dual extrusion for what we're doing here. Go ahead and slice this. And now let's preview. All right, so now we can see that we have that support scaffolding going throughout the center area. And it's a little harder to see, but over here on the side, you can see that it also is building supports up to the part we were looking at. So that'll support the upper portion of that slot so that that prints cleanly. And if we keep scrolling up, we'll see that these supports go all the way up. Now let's look in here. Look what happened. It's actually putting supports inside these tensioner pinholes. Not the end of the world. We could certainly pull those out with a pair of needle-nose pliers or something, but on some designs, you have things like cable channels where you really don't want supports. Those channels can kind of wind their way through a palm and that sort of thing, and you do not want supports going in there. So if you run into a scenario where you want to print with supports, where you need to print with supports, but you don't want them going in certain areas like this, Cura offers a nice tool called a support blocker. Now, I don't know that all the slicers will have this particular tool, but in Cura, it's over here at the bottom of the left-hand toolbar. It looks like you see here with a symbol with a box next to it. And if you click that and then click somewhere on your object, it'll just drop a little square like this. Doesn't look like anything much. Let's now deselect our object just by clicking off into the empty area here. And now we can select that cube object that was just put in here. See, it's just a small cube. That is an object which we can now move and resize and reposition however we need to. And wherever that object covers, it will block supports from being printed. So let's do that real quick. We'll stretch it out. We'll move it over here a little bit. We'll rotate it a bit to align it. Whoops, that's the wrong handle. Undo. I see it's the blue one I want. Okay, so rotate it a bit. And now let's stretch it out. Let's do non-uniform scaling so we can stretch it this way and we can stretch it back that way. And I don't really need it much taller, but we'll do a little bit like that. And now we'll move it because we want to make sure that it's not extending down into this area, because that will block the supports for that region underneath. Anything underneath that is going to get blocked. So we want to move it up until we can't see it underneath there, but so that it's still blocking those holes where we don't want supports. And there we have it. So if I go ahead and slice now, let's see what happens. So now if we scroll through the layers, you'll see that we still have our supports there throughout the print. But when we scroll up to the top, no more supports inside these tensioner pinholes, which is exactly what we want. So that support blocker can be a really useful tool. This is getting a little bit into advanced territory, but I'll also mention that these support blockers, once you add that object in, it can also be used in other ways. You can use that to change settings for specific regions of your print. So you could select that support blocker, and then this other tool, this icon here that has the 4 different types of shapes with different sorts of shading or patterns on them, click that. And now you can choose with your support blocker object selected and only that object selected, you can choose what type of mesh that is. Now, right now it's selected as don't support overlaps. In other words, support blocker. But you have three other options. Normal model, so you can just say that part's just normal, or you can say print as support, which means that anything overlapping with that will print as supports instead of as the object. So your object becomes sort of an indicator of where to put supports. You can get creative with that. And here's the one that gets really interesting, modify settings for overlaps. So you can click on that. And now you can say either infill mesh only or cutting mesh. Infill mesh, it means that whatever settings you choose will only affect the inside of the object. Cutting mesh means it'll affect everything that your tool here, the blocking tool, is passing through, including the walls, the shells, everything that's included within the boundaries of your object. So let's do cutting mesh. And then you can start to choose settings that you want to modify. Now, not all settings are available here, but a lot of settings are. And you can go through and see there's quite a few. This isn't the entire selection that you would have when you're modifying your settings normally, but you can change things like your line width. You can make the walls thicker in a certain place. We'll just throw a few of these in here to play with it. You might want to change the amount of infill. Let's see where that is. Infill density. You might want to change the infill pattern for a certain part of your print. Let's see, you can change things like your flow rate, your print speed. Maybe you want to go slower for a certain part of your print because you want it to be extra high quality. But let's just start with this. So I'll close this. So let's say for this upper portion where we have this tensioner block, for whatever reason, let's say we want this to be super strong. Let's say we want the wall thickness to be, instead of 0.8, we want it to be 2.4 millimeters, extra thick. And we want our infill to be 60% instead of the rest of the object, which is 30 to 40%. And let's change our infill pattern let's just do something like Cross 3D, which is not a typical one, but just so you can see the difference. Let's go ahead and slice now and see what happens. Okay, and now when we scroll through the layers, let's see what happens. On the bottom, we've got just what we had before, same kind of infill, same kinds of supports. But then when we get up into this top area, see what starts to happen here. You're seeing a lot more solid material. Let me zoom in for you here. So you can see that our object itself is a lot more solid. Get up in here where you can see it better. That portion up there is all solid because that's our 2.4 millimeters of wall thickness. We're no longer doing the support blocking function. So as of now, we have supports back in there, but we could throw in another support blocker to take care of that. But you'll see that up here, the infill pattern is, well, you can't see it too well because really all you're seeing here is the 2.4 millimeter thickness on the walls. There's not a lot of infill being used up here. So let's go back and change that real quick. And what we'll do is we'll just resize our support blocker and just make it cover more of our object. Okay, and now let's see. It's not going to affect much down here. But there you can see, just over here, you can see the new infill pattern that we specified, which is that Cross 3D. Let me get that in clearer focus for you. So you can see in there, it's doing this three-dimensional cross type of infill pattern, and you're seeing much thicker walls. You're seeing, there's that 5 or 6 extrusion line widths for the walls. So you can see that it's applying those different settings only to that region of the object. If we take a look at another part of the object, like these side portions here, you can see that it's using the previous infill pattern over there on the sides, in there. So you can see how that customization can come in very handy. You can drop these little, go back to the support blocker, you have to select your model, support blocker, click somewhere else to, I gotta be back in prepare mode. So this can be a really powerful way of customizing your prints if needed. Here's another example. Say we want those hinge areas to be extra strong. You can drop another support blocker in there. We would resize that support blocker. I won't take the time to do it now. Go in here, modify settings, same thing, make it a cutting mesh, maybe make the infill 100%, just print it solid. Or maybe even better than infill, maybe just do the wall thickness. because that way it doesn't even have, it's just going to fill it in solid with the outlines, which is a little bit stronger than using infill. So let's just go nuts. We'll just say 5 mm, which is obviously just, it's just going to fill up the whole width. And as you can see, that one little area there is being printed in solid, and it's doing it concentrically because it's just treating it as walls. There's no infill, so that would be nice and strong. And I would extend that to cover this entire hinge area if you wanted better strength. Back to our slides. Okay, now we've gone through and we've done our slicing, and we've set our settings according to the material that we're using, and now we are ready to send it to the printer. Make sure that you're using the right adhesive. This is so important because this has changed a lot. If you kind of got into 3D printing, early on, it was using Kapton tape, it was using blue painter's tape, it was using special print surfaces, it was all kinds of craziness. Nowadays, I don't think there's anything better than printing on a plain glass print surface with the right kind of adhesive. And my personal favorite is Magigoo. Now, there's a lot of options out there, and a lot of them are really good. So this is not the only option, but I've tried a lot of them, and I keep coming back to Magigoo because they have a number of different adhesives designed specifically for different materials, but their original formulation covers all the materials that we recommend for enabled devices. It's for PLA and PETG and ABS and a number of others. So it covers a lot of bases. And what's wonderful about Magigoo is you spread it onto your glass just like you would a glue stick, which a lot of 3D printers come with, and it takes just a couple seconds to dry. And then you print, and your prints stick, I think, much more reliably than a traditional glue stick. They really stick well. But the cool thing is that when the build plate cools, Magigoo is heat activated, so it releases its adhesion and the parts come off really easily. So I love using Magigoo. I use it on pretty much every print I do these days. So you might want to try that if you haven't already. I know it's a shameless plug because we do sell this at 3D Universe, but it really is wonderful stuff. It's going to depend on your setup. If you already have a printer that has, some printers have a PEI build surface, and that really works quite well with certain materials without any adhesive. But then again, you might have a type of a surface that if you don't use an adhesive, some materials will stick too well and you won't be able to get them off. So you really want to kind of think about your adhesion and pick the right adhesive. I love Magigoo, but there's a lot of others out there that you can play with as well. You also need to think about your environment. If your environment is too hot or too humid or too drafty, these things can affect your prints. So in some environments, you're going to want to think about having an enclosed build environment. Some 3D printers are fully enclosed, others are not. So that might be part of your thinking as you look at buying a new 3D printer. Having an enclosed 3D printer is a nice thing, especially if you get into these more advanced materials like PETG. And if you have an environment that tends to be more humid, having dry material is really important. It will affect your printing quality. So have a filament dryer on hand. There's a wonderful product called Print Dry. Yes, 3D Universe does offer this. In fact, we have their brand new version too, their Pro model that you see here in stock. So might want to consider that, but there's other solutions out there as well. Have a filament dryer though, so that you can bring your filament back to that proper health and proper humidity level before you give it to your 3D printer, and it will make all the difference in the world. On the left here, you see a print of a material that had obviously taken on a little bit too much moisture, and you can see very clearly visible print defects. And the problem is that a print like this, especially if you follow my cursor here around this particular layer, is where it's like it almost just didn't extrude material for a layer there. And that's where that part's likely to break there or split there. It's just not a very good quality to print. Not to mention, if it's printing this way, you can see these gaps and openings. You know that throughout the print, you have that same kind of inconsistency. So that whole infill structure is going to be less sturdy, and the part will be less sturdy as a result. On the right, you see the result of a properly calibrated printer, properly dried material, and this is the kind of print quality that you want to be looking for. What you're seeing there on the right is right off the printer, zero post-processing, absolutely no modifications. That's what it looks like after printing. Now, not every print will look quite that nice, but that's kind of what we're shooting for. Here's another example. With a large enough print bed, you can print all of the parts for an entire device in one go, or you can use multiple print jobs, just depends on your setup. But again, this is where the adhesion comes in really handy, because the more of your build plate that you're using, the more likely you are to have problems with adhesion, at least in my experience, because when you level your bed, it's going to tend to be really well leveled right in the center, but if there's any inconsistencies, it's going to tend to be out towards the edges. And so in my experience, especially with larger build plates, if I try to print where I'm just using like every inch of build space, those are the prints that have a tendency to fail, because most of it goes down well, but then you have like one part off in the corner that it just doesn't stick well in the first layer because the leveling isn't quite the same over there. So having the right adhesive applied makes a huge difference. As you can see, this is a print that was done using Magic Glue Original, and I have absolute confidence in filling my entire build plate when I take that approach. So once you get all your parts printed, it's time to assemble. And there you have it. That is my presentation. So at this point, I have no idea how I did on time here. I'm not good at sticking to, looks like about an hour, so good. So I wanted to leave time for a lot of Q&A and discussion and get into questions here. So let me, I'm gonna keep the screen sharing on, I think, because I might need to use that, but I'll turn off the spotlight. And Ben, if you want to start off with any questions you have, we can then open it up to everyone else.
I think there was a couple key terms in there. Maybe just to ask the folks that are here, were there any terms that you guys could use some clarification on? I know thermoforming, I did add a link into that. There wasn't so much description about thermoforming, so there's a little bit of info in the chat about that. Were there any other terms that anybody has some questions on?
On thermoforming, is there a part, I think there's a part, right, in the Phoenix hand that needs thermoforming to shape or something like that? Okay.
That's correct, yes. So if we, and I'll pull this up here, when you print this is a Phoenix hand that you're seeing here. That's how the arm guard or the cuff, that's how it prints here. It's a flat part, it prints flat. Now, the nice thing about that is, think about how the layers are going to be printed in this part. The layers are all going across flat. It's the whole thing from the bottom up. Everything is going to be printed with the layers, horizontal, right? Now that part is going to be thermoformed using the jig, which you see over here in the upper left. Okay, so you're going to use that jig to, you'll heat up the flat part and use this to form it on. And think about after that part's formed, your layers, think about the direction of the layers. They're going to follow the contours of the end part because of how it was printed. So you end up with really a really strong arm guard that way. That's the benefit. The downside is you have to do the thermoforming step. So some people don't like that, but there are multiple methods of doing the thermoforming. You can use hot water, dip it in hot water, and then take it out and form it, or you can use a heat gun. And we have multiple video tutorials that show how to do that, including the video tutorial that I did specifically for this hand, for the Phoenix hand, which does show clearly that thermoforming process. So take a look at that if you haven't seen it, and that'll show you the whole thing, including the 3D, the thermoforming and the assembly and everything.
Great. So it looks like Vivek had asked about bed leveling.
Okay. Yeah, if you can talk about that.
Well, bed leveling is critically important, but it's a little hard to talk about because it depends so much on the printer. Some printers are completely manual in terms of bed leveling. Some printers have assisted bed leveling, where they have like some sensors that'll probe the bed, and then it tells you, please adjust this screw or adjust that screw. And then, it'll check itself again and say, okay, everything looks good now. Other printers have fully automated bed leveling that can, again, probe the surface of the bed in a whole bunch of different points and then automatically make adjustments to level the bed, or at least compensate for any minor leveling issues. For example, I happen to like the Ultimaker printers myself, not the most inexpensive of printers, but wonderful quality. And so I'll just mention that the way they work is they come leveled from the factory. You don't have to level them at all. And at the beginning of every print job, it has this assisted leveling where it'll probe the bed in a whole bunch of different points. And it actually builds a three-dimensional height map of the whole surface, so that even if, glass is not perfectly flat, if you put it under a microscope, there are minor variations. what it'll do is it'll actually compensate by extruding more material in those areas that are slightly lower and less material in those areas that are slightly higher, just for the first several layers. And then it'll kind of shift back to printing normally. And you end up with beautiful first layers every time when you have that kind of capability. Some printers are a little more manual. And in that case, you got to make sure that your bed itself is as flat as possible. So if you're using glass, don't just go out and buy any sheet of glass, make sure that you're getting a really well-crafted, super flat, tempered sheet of glass, and make sure that it's as flat a surface as possible. Then go through your leveling process. When you level, most of the time your printer kind of guides you through the process, and usually it's a matter of checking the leveling in all four corners and then in the center or something like that. And when you're checking for the level, usually it's going to have you use some kind of a calibration card that came with the printer, or just a sheet of paper. If you just grab any sheet of plain paper, like a letter sheet of paper, standard office letter paper, standard thickness, you can use that as well for leveling. And all you do is slide that under the nozzle and then adjust your level while you're moving that piece of paper back and forth between the nozzle and the bed, and keep adjusting the level slowly until you can start to feel friction on that paper. You can feel the movement, but you can still move the paper. It doesn't grab at the paper. It's not biting down into it. And it doesn't leave a bite mark on the paper, but you can feel it when you tug on it. You can feel the friction. That's when you know that it's leveled properly. But having said that, I always find that even after doing the leveling routine, what you want to do is print yourself, run a test print of something, grab something that, as long as it covers as much of the bed as possible. It might be a simple flat square, or it might even just be an outline that goes around the outside of the bed. Just run a test job, and as it's going around, running the first layers down, watch really closely. Just use your eyes. And what you want to see as that first layer is going down is you want to see it being pressed into the bed so that it's being kind of smushed down flat by the nozzle as it goes over. You don't want the bead of filament to be sitting on top of the bed, like a perfectly spherical bead of filament. And and that means it's too high, there's too much space. If you see a little bead and it's not being smushed down, while it's printing, you can reach under and adjust the screw for that part of the bed, make it a little bit, raise the bed a little bit, and you'll see immediately in real time, you can see as it changes. And when you see that it's getting smushed out nicely, then you leave it. And as it gets to another part of the bed, you keep doing this. If you see that in a certain area, it's not extruding material, like it's kind of scraping the bed and only extruding a tiny bit of material, or it's even kind of no material, that means the opposite. Your nozzle is too close at that point. So you just move that screw a little bit the other way. And doing your fine tuning in real time using your eyeballs, I have found, is the best way for that final leveling step. So if you go through that leveling process, you should be good to go. You really shouldn't have to re-level much, at least if the printer is solid. You should be good for a long time.
Great.
Thanks.
I have a question.
Please.
When you show that the piece that John sent to you and you move it a little bit in the Z-axis.
Yes.
You said that you move it down a little bit. So some part of the model was out of the bed, and
That's
that
right.
part is lost, like
Let me
completely.
exaggerate it for you. And we put it down to -10 millimeters. And now you can see it more clearly. Yeah. Half of this object is now literally below the bed. And what the slicing software does is it just ignores all that. It just doesn't do anything. It just starts printing at the bed, which is exactly what we want. So the effective result is the same as going to your CAD software and slicing a flat plane and making sure that that flat plane is lying flat on the origin. I mean, yes, that's ideal. That's what you want to do long term, so that when you share this part with other people, they don't have to do this. But if you just want a quick fix, yeah, you can just drop it down a little bit and cut off the bottom.
Okay.
Jeremy, I wonder if you could show us a few devices, a few enabled devices, and then maybe talk about how printing is maybe different with different devices. If you could just pop up the catalog for a moment, or
Let me find, I have an album here. I just have to find it for a lot of these devices. I won't have all of them here.
because I know that some devices are much more complicated to print than others, and there's.
They are. So
Right.
this is like one of our more recent designs. This is the Kinetic Hand, and it's a beautiful design. but all of these hinges in here and the palm mesh, this covering here, are printed in flexible materials, and that can be tricky. Once you get your printer set up right, if you have the right kind of printer that ideally has a direct drive extruder, and you get the right material and you have the right settings, it's very doable. And so don't let me scare you away from this. We have a lot of people that are having a lot of success and are very consistent results, but it won't be like your first print out of the gate is going to be flawless. It'll take a little bit of experimenting and getting the right settings dialed in and that sort of thing. It's just a little bit trickier than other materials, and some printers are just not set up to handle it well. So it does depend on your hardware.
And maybe just to clarify too, so the white material is a different material than the black in between the digits. So there's a flexible hinge, which is printed in a different material than the white shell.
Yeah, of course. The parts are printed in a rigid material. In this case, I use tough PLA just for this test, but I would probably use PETG if this was for a real person. Let's see, we have, you guys are familiar with the Phoenix hand most likely. I'll come back to that in a moment. Here's the Osprey. Not a lot of people use the Osprey, but it's a very robust hand because it uses, the main difference here is that it uses these thick nylon monofilaments instead of two different types of cords. You don't have a non-flexible cord and a flexible cord to handle the finger movement. You have one set of nylon monofilament, which is a push-pull operation. So it causes the fingers to come in and it causes them to go back out when you bend at the wrist. And it also has leather components, as you can see here, for the part that goes over the arm as well as for the part that goes over the palm, which is very nice and durable, very comfortable for the wearer. So this was designed actually with with that sturdiness in mind. This was designed for an adult that with a lot of sort of heavy usage that needs something that would really stand up to a lot of wear and tear. What you're looking at here happens to be a print that was done in ABS and then treated with that acetone vapor treatment that I mentioned before. So that's why you're seeing that glossy, smooth surface. This was printed and then treated afterwards with that process. This is for that same gentleman that I talked about before. He likes it that way. He goes for that black glossy look. I don't know if I have recent photos of the Phoenix hand. So yeah, let me switch over. As you said, Ben, we could take a look at the hub for this.
Yeah, and some of the print times are very different in different hands.
Yeah, print time, there's so many variables involved when somebody asks you how long is this going to take, because it depends on the design, of course, but it also depends, of course, on scale. The larger you're printing the design, the more time it's going to take. But then there's a whole bunch of settings that will impact the time too. You can optimize your settings for print speed and get it done pretty quickly, or you can optimize your settings for print quality and strength, and it'll take a lot longer. That's what I tend to do. I don't care how long it takes. I optimize for the best possible quality and strength, and I'll just let it go. If it takes all day, if it takes 2 days, that's fine with me. So if we go to the device catalog, Enable Devices catalog in the hub, you can see that we have all sorts of different designs listed in here. There's a whole bunch of hand designs up here. There's a whole bunch of arm designs, a whole bunch of other designs, things like fingers and task-specific designs. And you can go into any one of these pages and you'll find all the information for that design. So it starts with a sort of a summary of how mature is that design, which means how good is the documentation, how well has it been reviewed by the community, the cost of materials, green being affordable, red being very expensive, popularity, which we base on how many times we've awarded badges for this particular design, how many people are making it, the difficulty, green being easy, anyone can do this, and red being very challenging. Maybe if we get into some of our bionic or powered devices, you would see those being higher difficulty. And then grip strength. Some of our designs have a stronger grip strength than others, and we feel it's important to sort of know that up front. So we try to share that with you in a sort of a low, medium, high factor. Then we give you a design, sort of a picture of what the design looks like. We give you a description, who the designers were, what the design is all about. And then we give you all the links you need to the STL files. In some cases, we share the source CAD files. When we have access to them, we share them. Sometimes a designer might not share them. That's up to the individual designer, but we make them available when we have them. links to any instructions or printable materials, links to assembly materials kits if those are available for this design, links to video tutorials, links to a color customizer tool that one of our volunteers built that lets you preview this design in 3D in real time and apply different color schemes to it and sort of get it to look the way you want before printing. Very cool. So
I wonder if you could pop that open actually for a second while you're talking about it.
Sure, sure. This device customizer, it's a great way of playing with and exploring and learning about the designs because you can kind of spin them around and look at them in 3D from all different angles and see what they look like.
The color customizer also allows a user or a printer to see all the different parts, the different components that can be adjusted for color. So sometimes kids are looking for, sort of superhero designs, or really any user might want to have, different colors to match different things that they're wearing. You can sort of play around with, the joints versus the palm and all the different components.
Yeah, it's a very cool tool. We'll include a link to this in the recording. But as you can see, there's a very large catalog here, and it would be worthwhile just browsing through it. Take a look at each one of the designs, go play with them in the customizer tool that we were just trying to look at. Maybe look at the documentation on some of them. In fact, I will call special attention to the Kinetic Hand, one of our newer designs, and just point out that this one in particular, if you want to see some beautiful documentation, it's included with the zip file that you download. But I'll pop it open for you real quick here, just to show you, because it's just, he did such a wonderful job on this. Oops. If there's any other questions while I'm pulling this up, please feel free to ask.
So yeah, I do have a quick question. So you mentioned the popularity indicator based on a number of prints that were made, but is it a good indication of the demand as well for that type of hand, or is it just what people print?
Probably not, unfortunately, because we can't even say that we're basing it on how many are being made, because we don't know. The only thing we know is how many badges are being awarded. So that's all we have to base it on. There might be a lot of people out there making it that aren't asking for badges. There also might be, like you said, the demand might not line up with that. It might be that there's a lot of demand, for example, for the Kinetic Hand because it's so attractive. It's just not, a lot of our volunteers aren't making it because it's newer and they don't know about it yet. So no, I would not say it's a good reflection of demand per se. I would say it's more just a matter of an indication of how many of our volunteers are making it. So okay. If I here go into the Kinetic Hand, and this is what I downloaded already. This is one of our Enable volunteers based in Australia, Matt Botel, and he just did a beautiful job on this documentation. It's so detailed. I'm gonna get to the interesting stuff and I'll slow down. Detailed diagrams throughout, explanations for all the different elements and concepts, parts lists, how everything goes together, silicone molding instructions. I've just never seen instructions like this. It's so thorough. I just wanted to give kudos to him and put this out there so that as we move forward, we can strive to make this level of documentation available to our community, because there's just some fantastic work that went into this.
Yeah, so getting back to my really level 0 question on how to avoid the second disaster, repeat the disaster with my first. What seemed to happen was not so much a kink, but just it seemed like because this spool is brand new and it's so full, right. These coils were unwinding and just coming off. And I think they got wrapped up around the axle, no pun intended, and just stopped printing. So I looked through the YouTubes to see if there's any simple fix, and I couldn't find anything. So I was thinking maybe just a little collar like this, so it just doesn't come off at the end, or is there any cleverer?
That certainly could help. I would, that looks like a fine solution to me. I would think some kind of a filament guide arm would also be helpful. And my guess is that you could probably find something like that on Thingiverse, because you mentioned earlier that you have a FlashForge printer, is that right?
Right.
So we can take a look and see. But what you want is if there's something that you could 3D print and then mount on the back of your 3D printer, a little loop that your filament would feed through on its way to the feeder or extruder or whatever it uses. That would help to kind of keep it coming straight off of the spool and prevent it from going off to the sides like it did. So you would want to go in here and just search for flash forge filament guide arm. I wonder if anything would come up for that. If not, we can get more general. It doesn't have to be flash forge specific. It might be a more general part. Other questions? Anything, especially 3D printed related. But yeah, this is the cool thing. You can use your 3D printer to 3D print modifications for your 3D printer. It's a lot of fun.
John, while this is loading, what printers do you have at the lab in Rochester?
We have Creality CR10S.
And there's two.
There's two. There's also an Ender. We also have one Ender that's living at Melvin's house right now.
Okay. And what are some of the common problems with those? Because it does seem like in moving them, you had to readjust the settings and it took some time to get them.
Right. Recalibration is an issue. Sticking to the bed has been an issue. Now we're using painter's tape. Jeremy recommends Magic Goo. That's all I got to say. But I've had adhesion be an issue. I also had filament breaking in the Bowden tube, which I think, Jeremy, check me on this, is just because it was old filament and gotten dried out.
Most likely, that's exactly right, especially with things that are more moisture sensitive, like if you're doing PVA or anything like that, it will dry out and get brittle and break. So if it's breaking in the Bowden tube, I would get fresh material. That's probably a humidity issue. And going back to Vivek, this is just an example here of one. I don't know if you have a finder, but here's the type of thing where you could 3D print just a new holder for the spool that feeds right into a guide there. There's a guide component that it feeds right up into, and that I think would prevent it from coming off the edges like it did. So you have a number of options to choose from. You kind of see what would work best.
Thank you.
And then John, yeah, if you give it a try, give the Magic Goo a try, it'll change your printing experience. It's really amazing. Any other questions? Well, maybe that's a good point to wrap then. We're coming right up on our 90 minutes anyway.
So I guess if people have watched this video later on and have questions for you about any issues, they can send you a message or?
Absolutely. Anyone is welcome to message me on the hub. That's probably the easiest way. If you prefer email, that's fine as well. We can use the eNable help desk for that because it's not just me answering those questions that way. So support@enable.org with the dash. So support@e-nable.org will always get you to our help desk, and you can submit any questions that you have there, and we'll be happy to help you with any issues that you run into. The hub is also fine. The hub is nice because if you don't even need to message me directly. You're welcome to, but if you post your questions in the forum, there's a whole lot of people that can help you in our community. We've got a whole lot of 3D printing experts, so that's even better and that way that the answers are then available for others as well. So posting it in the forum is a great way to do it. All right, thanks everyone. Bye-bye.